In this lecture, we look at some simple transformations such as scaling, reflection, and the inverse of these transformations. So scaling is enlarging an object or shrinking an object, and we can do this differently along different axes. For example, here we are only scaling the x values of the object, and here we are only scaling the y coordinate values of the object, and here we're only scaling the z. If we want to scale an object uniformly, we can keep a single s value for sx, sy, and sz. Now this type of scaling can still be achieved with a simple transformation matrix, which is again 4 by 4 dimensional and is it in homogeneous coordinate form. This is our original point and this is our scaled point. S is our transformation matrix, and we can define this S as a diagonal matrix where we put the X scaling at the top left corner, the Y scaling at 2, 2 location, and the Z scaling over here. If you multiply this with a given point or the set of all points of an object, the object will get scaled with these values along the S, X, Y, and Z coordinates. Now another simple transformation is reflection. In reflection, we can use the same scaling transformation matrix. Now we accept that we can use now negative values. For example, if we want to do a reflection along the y-axis, we put Sx is equal to -1 and we use Sy is equal to 1, and of course the Sz is also equal to 1. If we want to do a reflection along the x-axis, we set Sy is equal to -1. If we want to do a diagonal reflection, we want to do a reflection simultaneously along the x-axis and the y-axis, we set Sx and Sy both is equal to -1 and we get a diagonal reflection. Now if we want to go back to our original object, we'll need to do an inverse transformation. Although we could compute inverse matrices, the inverse of a matrix is generally a computationally expensive process. We can perform a simpler method to derive our inverse transformation matrix. For example, a translation matrix that did dx, dy, dz translation. We want to find out its inverse transformation matrix. That would be the same as if we moved the object negative dx, negative dy, and negative dz in the respective dimensions, and hence our inverse transformation matrix is simple to find. We just put negative values in the translation column. The inverse of a rotation matrix we can calculate by performing rotations by a negative theta angle. So R inverse theta is equal to R minus theta. This holds for any rotation matrix. Note that since cos minus theta is equal to cos theta and sine minus theta is equal to minus sin theta, R inverse of theta is the same as R transpose theta. Now transpose is easy to calculate compared to the inverse of a matrix. All you need to do in a transpose is to exchange the rows with columns and you get the transpose matrix. Scaling is also easy. If we had Sx, Sy, and Sz scaling initially, all we need to do is to get the inverse of Sx, so that is 1 over Sx, and inverse of Sy, 1 over Sy, and 1 over Sz to derive our inverse scaling matrix. So finding inverse matrices to perform the opposite transformation is easy. We can do it to calculating the inverse of the matrix, or we can find them easily using these simpler methods. Matrix concatenation. We can perform arbitrary affine transformations one after the other. by multiplying together rotation, translation, and scaling matrices. Because the same transformation is applied to many vertices, the cost of forming a single transformation matrix is easy. For example, if you were to transform a point P or a large set of points, first with D, then with C, then with B, and then with A, all we need to do is to calculate A, B, C, D, the product of these four matrices, and because they are all square matrices and they are all 4 by 4, our resultant matrix will also be 4 by 4. Now these are less computations compared to if we had to multiply D with 1,000,000 points and then C with 1,000,000 points and B with 1,000,000 points. The main part or the main difficulty in how to form a desired transformation from the specifications in the application is to work out how to or what type of transformation we should apply to get the desired effect, rather than calculating the matrix itself. The matrix transformation, the resultant transformation matrix can be easily calculated by concatenating the initial matrices and multiplying them together. The order of transformations. Note that matrix on the right is the first applied because that's the closest to the points. See, it makes sense. So if you were to multiply a large set of points P, or even a single point P with A, B, C, and we want to do this sequentially, we will first multiply C with P, and the resultant that we get will get multiplied with B, and the result of that will get multiplied with A. So mathematically, the matrices are applied from the right hand side first. Now you don't need to worry too much about this point, but if we represent our point as a row vector rather than our general convention of a column vector, then we just take a transpose of this whole system, and once we take a transpose of this whole system individually, the order of the matrices change like this. And also again P comes to the left hand side, but again then P gets multiplied with P transpose gets multiplied with C transpose first, and then that gets multiplied with B, and then that gets multiplied with A to give us the transposed new location of the point.